For this problem here, we have an object being kicked through the air, and we know information about its initial velocity, both the magnitude and direction, but the question really is just asking about what the magnitude of the acceleration is while the object's in mid-air. At this point, this should be automatic. We know that it's accelerating down at 9.8 meters per second squared. No matter how fast it's kicked, at what angle it's kicked, the only thing that matters is it's on or near the surface of the Earth. And if that's true, it's going to be accelerating down at 9.8 meters per second squared. Moving on to this next one, we have a projectile launched with an initial velocity of 80 meters per second at an angle of 30 above the horizontal. In the absence of air resistance, we want to know the horizontal component of the projectile's acceleration. This should be automatic here. We know that objects only accelerate down at 9.8 meters per second squared while they're in midair, and there is no horizontal acceleration, so that answer is just 0. Moving on to this next one, we have a situation where two spheres are launched from the top of a table. The table is 1.1 meters tall. We know that the one sphere, sphere A, is launched with an initial speed of 5 meters per second, while sphere B is launched with a speed of 1.5 meters per second. And they're both going to travel through the air and eventually hit the ground here. We should note that both spheres are launched horizontally. That is going to be a key thing here. So the first question is what is the time it takes for sphere A to hit the floor? So I'm going to go ahead and set up my chart in both the x and y direction for sphere A. So things I know here for sphere A, I know my acceleration in the x is 0 and negative 9.8 meters per second squared in the y. I know that it's launched with an initial speed of 5 meters per second, and that's also going to be the final because it's not accelerating in the x direction. And I know it's launched from a height of 1.1, so my change in y position is going to be negative 1.1 because I'm losing 1.1 meters of height. And I know that vi in the y direction is going to be 0 because it's launched horizontally. Okay, so now I can go ahead and start setting up an equation here, and I'm going to use the y side because I don't have either delta x or t on the x side. I know that I have to use that delta x equation on the x side of this. So I'm going to go ahead and use that first delta y equation. That first term does go away because our initial y velocity is 0, which means this won't become a quadratic. So I can say negative 1.1 is equal to 1/2 times negative 9.8 times t squared. And I can go ahead and solve for t. Negative 1.1 equals negative 4.9 t squared. And I find that my time here becomes 0.474 seconds. It asks for the answer to 2 sig figs, so I'm just going to say 0.47 seconds. And that's going to be my answer there to part A. Part B asks how long it will take sphere B to hit the floor, so I could go ahead and set up a whole new chart here, just like I did for sphere B. But if I think about it, the only thing that's going to change is when I'm dealing with sphere B, that 1.5 meters per second is going to become 1.5 meters per second. Everything else is going to stay the same in the case of sphere B. So that means that my time for sphere B is going to be identical, okay? Both spheres have the exact same motion vertically. They start from the same height, they have the same initial y velocity, and they have the same acceleration. So that means they're going to take the same amount of time in air. And this goes back to that idea of the independence of motion. And that simply tells us that that horizontal difference in motion, in terms of the initial velocity, has nothing to do with the vertical. So they still take the same amount of time to hit the ground. Moving on to part C, we want to know how far sphere A will travel from the edge of the table. And so I'm going to use my x information now. I now know my time, and I know my initial velocity in the x. So I can use that delta x equation. That last term, of course, goes away. And so we have delta x is going to be equal to 5 times that time that I found for part A, 0.474. And that means that my horizontal displacement here is going to be 2.37 meters. Okay, rounded to 2 sig figs, it's just going to be 2.4 meters. For part D, if I want to find the distance that sphere B travels, I do now need to actually set this one up because there is a difference in the horizontal velocity of these two spheres. So I'm going to use that same equation. That final term goes away once again. And so my displacement is just going to be 1.5 times that time, 0.474, and that gives me a horizontal displacement of 0.71 meters. And so that's my answer there for sphere B. Alright, for this next one we have a small plane that is flying at a distance above the ground and is trying to drop a package and have it land on top of a target. So we know that this plane is starting at a height here of 65 meters above the ground, and the plane is flying at 51 meters per second. And we are going to assume that it's flying at a level height and flying at a constant speed. Those are two things the problem isn't clear about, but otherwise this problem would be impossible. So we're flying at 51 meters per second. That means, and this is key, that package or that object that we're dropping is also traveling at 51 meters per second horizontally. And so it's going to go and fly through the air and land on the target here. So we want to know at what distance, horizontally, what distance should the plane drop that object so that it lands on the target. So I'm going to go ahead and set up my chart in both the x and y direction. So we know, of course, our acceleration, 0 and negative 9.8 meters per second squared. Okay, we know that our y displacement is going to be negative 65 meters because we're losing 65 meters of height, the package is. And it's initially traveling horizontally, so this is a horizontal launch, which means our initial y velocity is 0. In the x direction, we also know our initial and final velocity is going to be 51 meters per second. And it's the same for both because there is no horizontal acceleration. So I'm going to go ahead and set up some stuff on the y side because that's where I have most of my information to ultimately be able to solve for the time here. So I can say negative 65 equals, that first term goes away because there is no initial y velocity. So 1/2 times negative 9.8 times t squared. When I go ahead and solve for t, I find that my time here is going to be 3.64 seconds. Now that I have that, I can go ahead and solve for my x displacement using information on my x side. So on the x side, I have delta x is equal to my initial velocity, which is 51, times my time, 3.64. That term there with acceleration just goes away because there is no acceleration in the x side. And I go ahead and solve for this, and I get that my x displacement is going to be 186 meters. Okay, since it asks for 2 sig figs, we're just going to round that number here to 190 meters. Second question is asking about the location of the pilot when the package hits the ground here. So what we want to keep in mind is the package is traveling at a constant speed in the x, and so is the pilot. So every single time that the package has traveled some horizontal distance, the pilot has traveled that same horizontal distance, which means that when the package hits the ground here, the pilot is going to be directly above the package. So the answer here would be that first one, directly over the target, because both objects are traveling at the same x velocity. And this again gets at that idea of the independence of motion. The fact that the package is falling down has nothing to do with its horizontal motion. It's still traveling at a constant speed in the x, and so it will travel the exact same horizontal distance as the plane. Moving on to this next one, we have a sprinkler mounted on the ground, firing water at a speed of 14 meters per second at an angle of 20 degrees above the horizontal. That water is going to fly through the air and eventually land back on the ground here. And we want to know how far it travels horizontally before landing on the ground. So I'm going to go ahead and set up my chart in both the x and y directions. So with my chart, I of course know that my x acceleration is 0, my y is negative 9.8 meters per second squared. I know something about my initial velocity, but this 14 is at an angle, so what I'm going to do is I'm going to break it up into its x and y components. So that x component is going to be 14 cosine of 20, which gives me an answer of 13.16 meters per second. And that y component is going to be 14 sine of 20, which gives me an answer here of 4.79 meters per second. I can go ahead and fill those in for my initial velocities in both the x and the y direction. I also know that that velocity will be the same for my final x, because in the x direction we travel at a constant speed. I now want to think about some of my concepts, and I have a lot of options here. I know that at the peak, my Vy is going to be 0, and my time here is going to be half the total. So I could use that information about the launch, or I could use the fact that when it returns to the ground, my delta y is 0, and my Vy is just going to be the negative of my initial, so negative 4.79 meters per second. Really doesn't matter what you use. In this case, I'm going to choose to consider the entire launch, and so I am going to use that information that I know at the end. So my delta y is going to be 0, and my V final in the y direction is going to be negative 4.79 meters per second. So I'm ultimately going to end up using this y side to solve for time. I have a lot of information there, and that's going to let me find my x displacement, which is what I'm ultimately looking for. A few options for solving for time. I'm going to use the VFY equation, so I'm going to say negative 4.79 equals 4.79 plus negative 9.8 multiplied by my time, and I end up getting a time here of 0.977 seconds. I can then use that on my x side to go ahead and solve for information about how far the projectile goes. So on the x side, I'm going to use my delta x equation. I know that that final term goes away because my x acceleration is 0. And so my horizontal displacement is just going to be that x velocity, 13.16, multiplied by my time, 0.977. And I end up getting that my x displacement is going to be 12.86 meters. Rounded to 2 sig figs, as the question asks, it ends up being 13 meters. Next question talks about Alan Shepard, an astronaut, hitting a golf ball on the moon. And he hits this golf ball at a speed of 27 meters per second, and it's at an angle of 36 degrees. Golf ball is going to fly through the air and eventually land again on the moon. We do want to keep in mind that the acceleration due to gravity on the moon is 1/6 of its value on Earth, so 1/6 of 9.8. But the way we're going to do the problem is not going to change. So I'm going to start out with two things. Number one, I'm going to set up my chart. Number two, I'm going to break that angled velocity into its x and y components. Starting with my chart here, I still have 0 acceleration in the x direction, even on the moon. My y acceleration is going to be negative 9.8 over 6, or negative 1.63 meters per second squared. I can go ahead and split that initial velocity, that 27 meters per second, up into its x and y components. So the x component is going to be 27 times cosine of 36, which gives me an answer of 21.8 meters per second. And my y component is going to be 27 times sine of 36, which gives me an answer of 15.9 meters per second. Now that I have that all set up, I need to think about my concepts. I know at the peak my Vy is 0 and my time is half the total time. So those are two concepts that I could use. I also could use the fact that when it returns to the ground, my delta y is 0 and my Vy is just the negative of my initial. It doesn't really matter what you use. In this case, I'm just going to use the time going up to the peak, but you could, of course, use the total time. So I am going to go ahead and use my VFY equation, so I can say that 0, my time, or my velocity at the peak, equals 15.9 plus negative 1.63 multiplied by my time. I go ahead and solve for that time, and I get that this object is going to be in the air for 9.72 seconds. However, that's only the time to the peak, so I need to multiply by 2, and I get my total time, which is going to be 19.4 seconds. Rounded to 2 sig figs here, I just get 19 seconds. Now that I have that time, I can figure out how far it traveled in the x using my x information. And so I end up getting that delta x is equal to my initial velocity in the x, which is 21.8 multiplied by my time, which I just found. Then I'm going to use that total time of 19.4. So I end up getting an x displacement here of 424 meters, which rounded to 2 sig figs just becomes 420 meters. The third part asks about how much further this object would travel on the moon than on the Earth. So I'm going to go ahead and think about how far it would travel on the Earth first. And really the only thing that changes here is this acceleration. If I'm thinking about it being on the Earth, my acceleration is just negative 9.8 meters per second squared. But that means I can basically repeat this calculation and just change that acceleration. So on Earth, I'm going to have 0 equals 15.9 minus 9.8 t. And I go ahead and solve for my time here and end up getting a time on Earth to the peak is 1.62 seconds. Multiply that by 2, and I end up getting that the total time on Earth is going to be 3.24 seconds. To get my horizontal displacement on Earth, I'm going back over to my x side. That x acceleration is 0. And so it's the same calculation as calculation 2 here. I'm just going to use that new time that I just solved for. So I have delta x is going to be 21.8 multiplied by 3.24. And I find that my horizontal displacement on Earth would be 70.7 meters. And now I just want to find that change. So delta x moon minus delta x on Earth. And so that's going to be 424 minus 70.7, which is going to give me 353.3 meters. Rounding that to 2 sig figs, I'm just going to have an answer here of 350 meters. Alright, so moving on to this one, we have a physics student on some foreign planet, Exodor, which means acceleration due to gravity is not 9.8 meters per second squared. And we have them throwing a ball, and this is the path of the ball here. We know a few things about the velocity. We know that at time t equals 1, the velocity has an x component of 2.0 meters per second and a y component here of 3.0 meters per second. And we're asked about the x and y components of the ball's velocity at 0 seconds, at 2 seconds, and at 3 seconds. So I'm going to focus in on my graph here. I know from my concepts that each of the velocities, each of the x velocities, are going to be 2.0 meters per second because in the x direction, the object experiences no acceleration. I also know that at the peak, my y velocity is going to be 0 meters per second because that always happens at the peak, even if it's on a foreign planet. And I also know that because these two, 1 second and 3 seconds, are at even heights, okay, that my y velocity at 3 seconds will just be the negative of at 1 second. So with my concepts, I can fill in a lot of my information. The only thing that's missing here is my y velocity at the start. So there's two ways of thinking about this, okay? One way is I know that it's accelerating at a constant rate. So it starts with some y velocity. At 1 second, it's dropped to 3 seconds, meters per second. And by 2 seconds, it's dropped to 0. That means I must have started with 6 meters per second of velocity because it's losing speed at a constant rate. Now, the other way of doing this is I can consider the portion of the flight just from that 1 second up to that 2 seconds. And I can actually go ahead and set up an equation to solve for my acceleration, thinking about my initial and final velocities for that period of time. So my final velocity is going to be 0, my initial is going to be 3, and my time is just 1 second, which means my y acceleration here is negative 3 meters per second squared. And so there I see what my y acceleration is, and if I really wanted to, I could set up another equation to solve for that acceleration at the very beginning. Now I'm going to go ahead, though, and be considering the entire flight from 0 up to the peak. And so I can say that my final is still 0, and that's going to be equal to my initial, which is what I'm looking for, plus -3, that's my acceleration, and the time it takes to go from the ground up to the peak, which is 2 seconds, which means my initial y velocity is 6 meters per second. So I can do it in a more rigorously mathematical way, or I can just think conceptually about the fact that it's slowing down at a constant rate, which means that from here to here it's losing 3 meters per second of velocity. So from 0 to 1, it also must have lost 3 meters per second of velocity, making that initial velocity be 6. Now that I have solved for all those components, I can go ahead and answer the first few parts of this question. So for part A at time 0, my components are going to be 2.0, comma 6.0. All right, at 2 seconds, which is part B, they're going to be 2.0, comma 0.0. All right, both expressed to 2 sig figs. And for part C at 3 seconds, it's going to be 2.0, comma -3.0. I also was able to determine my acceleration in the process. I solved for that right up here, and that acceleration ends up being -3.0 meters per second squared. Again, I can solve for that mathematically or just by looking at the fact that it's losing 3 meters per second of velocity every second. The last part asks for the angle of the ball's launch, and so I'm going to think about that initial velocity where it's traveling at 2.0 meters per second in the x direction and 6.0 meters per second in the y direction, and I can use that to solve for my angle. Knowing that tangent is just opposite over adjacent, I can say tangent of that angle is going to be equal to 6 over 2, which means the angle is going to be the inverse tangent of 6 over 2, and that gives me a launch angle here of 71.6 degrees. Rounded to 2 sig figs, it would just be 72 degrees. And there's my answer to part E. Moving on to this next one. This one can be a little bit tricky, but we have a tennis player hitting a ball that's initially 2 meters above the ground. And we want to know whether or not it will clear a net that is 1 meter above the ground and located a horizontal distance of 7 meters away. Okay, and so that ball we know is hit at a speed of 20 meters per second at an angle of 5 degrees above the horizontal, and it's going to fly through the air and do something like that, and it may or may not clear the net. So what I'm going to do is I'm going to figure out how far it drops in that time. I'm going to solve for this delta y, and that's going to determine whether or not it will have enough height to clear that net, which is 1 meter high. So I'm going to first set up my x and y charts and also go ahead and solve for my x and y components of the velocity. So looking at my chart, I of course know my x acceleration is 0, my y is -9.8 meters per second squared. I do know my x displacement is going to be 7 meters. Okay, and I can go ahead and break that velocity into its x and y components. So the x component is going to be 20 times cosine of 5, which is 19.9 meters per second. That y component is going to be 20 times the sine of 5, which gives me a y component here of 1.74 meters per second. I can fill that in as the Vix. It's also the Vfx because there's no x acceleration. And in the y direction, I can fill that in as the Viy. Now I do need to be careful. I don't actually know my delta y. I can't say it's -1 because I don't know for sure that it ends up even with this net. That's what we're ultimately going to be solving for. And so in this case, I'm actually going to start with my x direction because I have more information here and I'm going to be able to find my time. So in the x direction, I use my delta x equation. I know that that final term goes away, and I have 7 equals 19.9 multiplied by my time, which means the time that the ball is in the air before it travels at 7 meters horizontally to the net is 0.351 seconds. Now I'm going to go over to the y side and solve for my y displacement using that delta y equation. And so I get that delta y is going to be the initial velocity 1.74 times 0.351 plus 1/2 times -9.8 times 0.351 squared. I go ahead and plug that into my calculator, and I get a y displacement here of 0.007 meters. So what that means is that the ball ends up 0.007 meters above its initial point. Okay, so it actually didn't drop at all by the time it made it to the net. It was still just slightly over that initial height of 2 meters above the ground. So that means, yes, the ball will clear the net, okay, because it will be at a height here of 2.007 meters. To answer that second question, I'm going to start with the fact that the height now is going to be 2 meters plus that change in y, that 0.007, or 2.007 meters. Okay, so the second question says, by how much does it clear the net? Well, it's at a height of 2.007. The net's at a height of 1, so it clears it by a height of 1.007 meters. That's how far it is above the net when it goes over. So my answer rounded to 2 sig figs would just be 1.0 meters. For this next one, we have a cannon firing a cannonball at a wall as shown, and it hits the wall at some point here up near the top of the wall. And we want to figure out how long it takes to get there and what height it has when it hits the wall. So I'm going to set up my chart in the x or y direction once again. So I know my x acceleration is 0, my y acceleration is negative 9.8 meters per second squared. And I can go ahead and take that initial velocity and break it into x and y directions. So I have 89 at an angle of 40, so that means the x is going to be 89 cosine of 40, which gives me 68.2 meters per second. I know my y is going to be 89 times the sine of 40, which gives me 57.2 meters per second. And so those become my initial velocities in the x direction, also my final in the x, and my initial velocity in the y. The last thing I know is my horizontal displacement. Distance to the wall is 300 meters, so I can put that in for delta x. I'm going to go ahead and start with my x side and use that to solve for my time that it's in the air. So I can say 300 is equal to that 68.2, which is my initial velocity, times t. That whole final term goes away on that side, and so I end up getting a time here of 4.4 seconds. That's the time it's going to take to hit the wall, and that answers question A here. For question B, I'm going to go ahead and solve for my delta y. So I'm going to say that my delta y is going to be the initial y velocity, 57.2, times that time, 4.4, plus 1/2 times negative 9.8 times 4.4 squared. And I go ahead and find that my y displacement, which is going to be how high it is above the ground, since it started on the ground, is going to be 156.8 meters. And that's going to round, if we're only doing 2 sig figs, to 160. And so that's going to be my answer there.